So now we are kind of making our definition of measurable sets more general. You can actually imply very strong results for any open set. We can get the inverse image will be continuous. It will be a measurable set. So now suppose I have a continuous function, and then I have g to be we say e to be measurable. Then the composition of g and f is measurable. Okay, remember, be aware that the inside g is measurable, the outside f is continuous, and the proof of this is super easy. You just look at this set. You just look at this set, right? To see if this is a measurable subset of E. And by the way, this just means all the points in E such that f of g x is bigger than t, right? And this is what? It's just all the x such that gx is inside the f inverse of so what t this. Okay. Well, I can also say this is just the g inverse of f inverse of t positive infinity, right? So don't be confused with this. This is just the interval in R. This is just the range of the functions. And the f inverse of this will be open because f is continuous. The pre-image or inverse image of an open set under a continuous mapping is still open. So this whole thing here is open. Okay? And if g is measurable, then the inverse image of this open set will be measurable. So that means this is measurable. Well, what we showed is that this is measurable, so that's why the composition is measurable. Okay, so this is important, that f has to be outside, g is inside. If you switch these two, it's not necessarily measurable anymore. Okay, so that's the remark I want to make. If g is measurable, f is continuous, then this is not necessarily measurable. Okay, but we can still make the continuous function inside. The only requirement we need is that the continuous function has the following property. Okay, suppose I have a function t from Rn to R to Rn even, and it is continuous. And for any it's continuous, and the t inverse of z, the measure of this, will be equal to 0 for any z in Rn with measure 0. Okay, in other words, if z has a measure 0, then the t inverse or the pre-image of z is also has a measure 0. Okay, remember that this t is from Rn. T is from Rn to R, and so it will map z to t of z. Okay, or in other words, I should say, if there's a set of z in Rn, then it will map this set to z. Okay, and the problem is that if z has a measure 0, then this must have measure 0 as well. if T has this property, then we can put T inside of a measurable function, and the composition of the two is still measurable. Okay, in this case, we put the continuous function inside. Okay, and we can still show that this is continuous. And the proof is, so what we need to do is to show that this kind of set is measurable, right? We need to show this is measurable. Okay, and then for any, to show this measurable, according to the lemma we showed earlier, if we can show this is measurable for any open set, that will be fine, right? So for any G open Rn open R in R, I know that f inverse of G is a measurable set. Right? This is because f is measurable, so the inverse image of G is measurable. And because of that, we know it's a measurable set. I know that there exists a G delta set. I hope you still remember. It's just a intersection of countably many open sets. There exists some H such that the G is in H. Sorry, the F inverse of G is in H, and the measure of F inverse of G is the same as H. Actually, the difference of the two, let me rewrite this part. The measure, sorry, again, this, the measure of this H minus the inverse of G is 0. Okay, it just means that we can have a G delta set H that includes this set, and the measure of their difference, or this minus this, is equal to 0. So it's equal, they have equal measure. All right, and now you can say that we let Z to be the H minus F inverse of G, then the mu G, as we said, this is equal to 0. And hence, the T inverse of Z should have a measure 0 as well. This is a property of T we know. The inverse image of Z under the T has a measure 0. And now you can we can work on the T pre-image of this F inverse of G, and this is as we showed earlier, this is equal to T inverse of H minus Z, because H, this is like the H, this is like the F inverse. Let me show this. This is the F inverse of G, and we basically have this H. That I'm showing this, but the H is actually almost as tight as possible, and the part here is the Z, and it has a measure 0. The Z has a measure 0. Okay, so that also means H minus Z is the inside here. Okay, and it's a subset. The Z is a subset of H, so this is just a T inverse of H minus the T inverse of Z. Okay, and we know that because this this one has a measure 0, and this set this set, you can see that this H is a G delta set. So the T inverse, the inverse of the inverse image of H under T will be measurable. Right? Because this H can be written as a composition of open sets and so H is intersection of open sets. We use GK. Each one is open. So the T inverse of H is just the T inverse of this open sets. And it's just the intersection of T inverse of GK. K is from 1 to infinity. And here the GK is open, so you have this T as a continuous function. So this one is still open, right? Open set, the inverse map or inverse image and of a open set under a continuous mapping is still open. So this is open, and the intersection of the open sets, this is just is still a G delta set. It's a G delta set. So that's why it must be measurable. So that's why this one is measurable. And this must be measurable because the measure of this is equal to 0. So it must be measurable, and the difference of this two must be measurable as well. And that shows that this side here is nothing but just the inverse of the composition of F and T. And now we show that for any open set G, this the inverse image of G is a measurable set. So that means F, composition of F and T is measurable. Okay. So a easy corollary of that is now you can see that as long as your continuous function t here doesn't map a set with positive measure to a set with measure 0, then we can put the t inside F. This is measurable. This is a continuous t, and the composition of it will be still a measurable set. It will be still a measurable function. And a corollary of the result here is that if F is measurable, and T is a linear degenerate linear transformation, or is just I'll say in general just to be a non-degenerate degenerate transformation. Then the composition of the two is measurable. Okay, so the non-degenerate mapping here just means that the determinant of T is non-zero. Okay, the easiest case is T, for example, T is a non-degenerate or non-singular matrix, square matrix. Then T will be non-degenerate because the determinant of T will be non-zero. Okay, and I don't even need to prove this because in this case, if Z has a measure 0, then it must imply that the inverse image of Z under T is 0. Because if it's not 0, then after you map it using T, it will end up with a set with non-zero measure because the T itself here is non-degenerate. Okay, determinant is T, so a determinant is positive, so it will keep the mass, you only scale the mass by a positive constant, but will not change something with positive measure to something with measure 0. Okay, so the proof is really simple here, so I will skip this. A final example of the corollary here is that suppose I have a function f is from R2, say from Rn to R, it's measurable. Then if I define a new function g of xy to be f of x minus y, and this mapping, as you can see, this is mapping from Rn, the Cartesian product of Rn and Rn to R, because it maps every x and the y to f of x minus y. Right? So this is what the function g is defined, and this function g is measurable. Okay, the proof is if we can show g is a composition of a measurable function and a non-degenerate transformation t, then we're done. Right? This is what the approach is. So we define this hxy to be the function of f of x. Okay, so this h you can see is Rn into R. But the point is that if this is xy, it doesn't depend on y at all. You just map this to f of x. Okay, and as you can see, let's consider the stat h is bigger than t. And this, again, this just it just means that it has two arguments. It's just all the x and y in Rn by Rn. The h of x y is bigger than t. But this one is just equal to f of x, right? So this set here is just equal to the set where f of x is bigger than t, and y can be anything, cross product with Rn. Okay, and because f is measurable, so this one is measurable. And apparently Rn is measurable itself, so that's why this whole thing is still measurable in Rn by Rn. Okay, it just means that this is still a measurable set. Well, it's a measurable set, that means h is a measurable function. So h is measurable. All right. So we have the h here, and how do we get h to get from h to g? We just need to make this x as x minus y, because if we have that, then this becomes x minus y here, and this is just equal to g of x y. Okay, so I can define my transformation t of x and y to x minus y and x plus y. So my t is mapping Rn by Rn to, again, Rn by Rn, and the transformation is made by this. Okay, and apparently this t is non-degenerate. Right? If it's 0, that means if the result is 0, then that just means the point itself is 0. So t is non-degenerate. Okay, and it's apparently is continuous. So by the previous corollary, we know that the composition of f and t, also h and t, but this h and t composition of H and T is just G, right? It's measurable. Okay, the reason it is composition of that is just because this G of X Y is equal to F of X, but on the other hand, H composition of H and T on X and Y is just H of T X Y. And according to the definition of T, it's just X minus Y and X plus Y. But according to the definition of H, that just be F of the first argument, which is this. So that's why, sorry, this one is X minus Y. So that's why these two functions are the same. So that's why I have this, and I know that the right-hand side is measurable, so the G is measurable. Today we start with a new chapter about Vega integrals. So this is an important part of the Vega theorem, or the measure theory, which is an extension of the Riemann integrals you learned in calculus. So the whole theory is based on the Vega measure and the Vega measurable functions we learned in the previous two chapters. So first of all, we introduced the Vega integral, or integral of simple non-negative functions, because the integrals of this kind of functions are really easy to define, and they are very intuitive. So the definition for such type of integrals is given by this. So suppose we have a function f. It's a mapping from Rn to this. So it's negative, can take infinity as the positive infinity as the value, and it's a simple function. We know from the previous chapter that the simple function f means that it can be written as a piecewise constant, where this Cauchy ai is a characteristic function for the area ai. It takes the value 1 over ai and takes the value 0 if x is outside of ai. And over this region ai, it takes the value ci. Okay, so that's why we call it a piecewise constant function. So this ai's is a disjoint union of the entire space Rn. So we sometimes, just for simplicity, we just denote this Rn by x, capital X. It's a disjoint union, means that these are disjoint sets, they're mutually disjoint, and the union of them is the entire space Rn. So it's like you partition this into disjoint sets. Okay, and we assume that every one of them is measurable. Okay, every one of them is measurable. And then for any measurable set E, which is a subset of the Rn, or this x, we can define the integral of this function, piecewise constant function, or this non-negative simple function f on E by this. So we denote it by this integral of f with this dx, d mu of x. You probably see this dx in calculus, but right now we need to specify which measure we're going to use in the integral. So since we're using the Vega measure here, so we specify that to be the mu of x. If you're reading a paper or reading a book that discuss the Vega measure, then this is probably just dx. But in general, we could have other type of measures defined, like in our next chapter, we'll define the radon-nicotine derivatives of the measure. So in that case, we could have different measures defined, then we need to specify which measure we're using now. Okay, but here for this chapter, we only consider the Vega measures. And now we have the function f, we have the measure, then the integral of that over the set E can be written as this. It's defined to be this. So you can see what the meaning of this. Here, suppose we have this, as I said, if I draw the picture, this is the entire x, which is equal to Rn. And I said we partition this into maybe different parts, okay, like this. And then this is like A1, A2, A3, A4, A5, A6, and even more. And the E could be like this, say here. So the circle is a set E. So we will consider the integral of the function over E. We need to partition this E using those AIs. We know that we can do this partition because the AIs is a disjoint union, can form a disjoint union of the entire X. So you can separate, or they can partition this E as well. And then on each of these pieces, for example, here the intersection of E and A1 is this area, and we're just going to multiply the area here, which is defined by the measure times the function value over this area, which is C1. Okay, so this area will give us C1 times the measure of the intersection of E and A1. And similarly, we can take the area here and multiply by the C2. So it's like the, this is kind of the integral of a piecewise constant function. If you were in 1D, we know this is the A1. Then the function value is this, then the integral is nothing but the C1 times the area of A1, which is the measure of A1. Okay, and this is just in 2D case, and it can be in n-dimensional Euclidean space. Okay, it's very intuitive to define the integral for this type of functions. Okay, we often write this integral in a shortcut form. So this is the one notation we just used here, and we know that this is nothing but just the integral of f times the characteristic function of E over the entire X. Okay, because this E will restrict yourself to this function will restrict yourself to E only, because outside of E just 0, and the integral of that over those area will be 0 when we multiply to X. Okay, and sometimes we write it in just this way because it's very clear what this means. And sometimes we even ignore the d mu part if we're always using the Vega measure, okay, like in this chapter. Okay, so these are the definition. This is a definition for the integral of simple non-negative functions. One thing that you need to be careful is that if if ci is infinity and this part is non-zero, is positive number, then the multiplication of these two will be positive infinity. And in that case, the integral will be definitely positive infinity. But if the ci is infinity, but this part is 0, for example, if the function f is finite almost everywhere, then we know that over the area that ci is infinity, the measure of ai will be 0. Then you take the intersection with anything, will be still a measure 0 set. In this case, we will be multiplying infinity and 0. And as we introduced in the last chapter, we consider this case as 0, the multiplication of these two as 0. Okay, that means even if the function takes the value infinity over a set, but as long as the set has a measure 0, we can just ignore it. Okay, it doesn't affect our integral. Okay, and also if the measure of ai is large, or measure of this is infinity, but this is 0, then we still multiply them together to get 0. And in that case, it just means that if it's 0, if the function is taking 0 there, then the integral doesn't count at all. Okay, so these are the two cases which involve the infinity. By they don't affect our result. Yeah. Okay, let's take an example. So consider the Dirichlet function. Now this is a very famous function in analysis. So a function f of x is defined to be to have a value 1 if x is a rational number. Let's only focus on the definition of f, or restrict f to the interval 0 to 1. Okay, so over the interval 0 to 1, the function takes the value 1 if the x is a rational number, and it takes the value 0 if it's an irrational number. Okay, and then the integral, as we can see, this is a simple function because the f of x can be written as 1 times the c of q 0, 1 of x plus 0 times the c of 0, 1 minus q, right? And this is like the a1, this is like the a2, to only partition the interval 0 to 1 into two parts. So this is like the a1, this is like the a2, and this is like a c1, this is like the c2. Okay, and then taking the integral over the entire interval 0 to 1, it's the same as we showed earlier, is taking this the c1 multiplied by the measure of this a1 plus 0 times the measure of c2, measure of a2, which is q 0, 1 minus q. Okay, and now you can see that this gives us the rational numbers over interval 0 to 1, so the measure will be 0. Right? We showed that for countable set, the measure will be 0. So this is just a 1 times 0. And for here, this part gives us, well, we already have 0, so it doesn't matter what this one is, it always gives us 0. But just to be clear that this part is the set of irrational numbers over inside the 0 to 1. So the measure of this is equal to 1. So the value is 0, but the measure here is 1, but the sum will be still 0. Okay, so this function the integral of this function can be easily obtained using the definition of the Vega integral for non-negative simple functions. But if you still recall, this function does not have a Riemann integral. The Riemann integral of this function does not exist. Okay, and because the reason is because the Riemann integral was defined, if you still recall, the Riemann integral was started from the Dabon sum, Dabon upper bound, Dabon lower bound, which means that you first need to partition, let me write it this way, the Riemann integral is that you have a function f defined on the interval 0 to 1, or in general you can have interval a to b. Then partition, so the first step is to so we're trying to take the integral of this dx. The question is what it is, and you know that step 1 is to partition 0, 1 into this delta. So let's say the delta. Then you set x0 to 0, and then x1. Eventually have x maybe capital N is equals to 1, right? And the second step is to find a Dabon sum. So compute the delta the upper S delta to be the sum of I from 1 to capital N, and then you need to multiply the maximum value of f of x over, right, xi, x between xi and xi minus 1 and xi, and multiply this by the length, which is xi minus 1. And you also need to compute the small s delta, which is the same thing except that the maximum is replaced by the minimum. Right? And the third step is, you consider the upper integral of f, and that is defined to be, defined to be the supremum, the infimum of this s delta for delta length going to 0, right? This delta, the absolute value of delta means the largest, the longest segment in your partition, and also the lower integral is defined to be supremum as delta goes to 0 of the little s delta. Okay, and then we say that this integral of f exists if the upper integral is equal to the lower integral. That's what we did for in this case, if they are equal, then we say that the Riemann integral exists and that the value of the Riemann integral is equal to the value of these two, right? That's how we define the Riemann's integral. But the problem with this is very intuitive, because what we're actually doing is that, say for a 1D case, we have from 0 to 1, but generally it could be from A to B, and you have this function, and what this Riemann integral is doing is you first partition this, and then you get these things, and then for each segment you do the largest integral, largest rectangle that includes this, and also the smallest rectangle, right? Then you take the sum of the largest rectangles together. That will be your capital S, right? That will be the you always take the largest rectangles. You get this capital S, and you always take the smallest rectangles that is inscribed into this each of these pieces, and it's a small s. And then you take the limit. But in this case, you can take the infimum or supremum because it's a monotone when your delta goes to 0. So you can take the infimum, you can take the supremum here, and that will be your upper integral, the lower integral. And if these two agrees, then we can say that function is Riemann integrable. And the Riemann integral is defined to be the common value of them. And apparently, if you apply this to this function, you will see that these two are not equal. The reason is because it doesn't matter how you do the partition. And over the partition, the maximum value will be always 1, as you see here, because it doesn't matter what partition you have, there will be always a rational number in between, and you take as maximum, you will always get 1. And you will always get 0, because over any interval there will be irrational numbers. So this is always 1, this is always 0. So you take the infimum, you take the supremum, that's still 1 and 0. So that's why these two will not be equal, and we cannot have Riemann integral defined on that. But now you can see the situation is much easier. Okay, in the definition of the Vega's integral can give us the result very easily. Okay. I think when I was learning this, my professor actually told me a very intuitive way, which is what not he said, but Lebesgue said about this idea. So compared to the Riemann's integral, the Lebesgue's integral is like considering the case you owe somebody lots of money, and you want to pay him back. So what you're going to pay is that if you have a bunch of cash inside in your hand, but they have different values, $1, $10, $20, $5. So you just have a bunch of those money, and you know that the money is enough. It's exactly the amount that you're going to pay back. Then when you meet this person, how you're going to pay them is you just pick up one bill from your purse or wallet. You pick out one bill every time in the payback. So maybe this time you get $1, next time you get $5, and next time you get $20. So it's like just like this case, right? You just pick up bill one by one, and whatever you pick up, you just return it. So this is like this case. For Lebesgue's integral, what you do is you first sort up the bill, and you put the $1 in one pile, the $5 in one pile, the $20 in one pile, and then you just need to count how much you have on each pile, and then sum together. So this is like for the first pile, the C1 is one. If it's $1, you just say one, and you count the area, which is the number of bills you find in that. Maybe you have 50 of those, and so the C1 will be 1, the area will be 50. Then you multiply them together, you know that you have $50 in this pile. And in the next pile, you probably have $5, but you won't have seven bills. Then together, that's $35 in that pile. So you just sum them together and then pay it back. Okay, so it's the same thing. You just look at it in different angle, and that makes things change. And that is the difference between the Riemann's integral and the Lebesgue's integral in the layman language. Okay, so you can sometimes think in this way. You first figure out the area or the set where the function takes the constant that takes the same value. You just need to multiply this value by the area of this set, and then you put them together and add the next one. Okay, just a slight history about the development of this Lebesgue integral. Okay, so this is the one example. We can consider another example, which is the property of the Lebesgue integral is that this integral is still satisfies all the properties we would expect for an integral to satisfy. So the first is linearity. So what that means is we have two functions. The integral of the sum of these two functions is equal to the sum of the integrals of each one of them. Okay, so suppose f and g are mappings from Rn to R, and they are simple. So for now, we just consider simple functions, simple non-negative functions. Okay, and always assume they are measurable for sure, of course. Then for any constant c and the measurable set E, there are the integral of c times f over E is the same as c times the integral of f. and also the integral of the sum of f and g is equal to the integral of f over e plus the integral of g over e. Okay, the linearity of the integral. And the first one is obvious, right? We can easily show that if f is written as a simple function, it's the sum of those piecewise things. This piecewise constant, they multiply c, just multiply the constant, each constant ci by c. In the, you can easily get this one. So now we just show this one here. Okay, suppose f x can be written as this kind of piecewise constant function. We got it the ci, maybe ai times c ai x, and this gx is written as another piecewise constant function, which is j from 1 to q. And p and q are natural numbers. It's a number of partitions we have. bj, c, b, j, x. Now, the integral of these two functions, according to the definition, this is just according to the definition, the sum of these two functions is still a simple non-negative function. It's still piecewise constant. And the integral of this is nothing but the sum for I from 1 to p, j is from 1 to q, and then we have the ai plus bj over the area which is the intersection of e and the ai and bj. Okay, and this is because the sum of these two will give us another non-negative simple non-negative function, and that is just let me write it out. Just the sum of ai plus bj times c ai bj x, where I is from 1 to, should still have double sum. This, right? That's why we can write the integral using the definition. And then we can separate this ai and bj's. So for example, we can take the sum of this e ai bj plus the sum bj ai bj. And now we have, so we just simply split ai and bj. And now we have the liberty to do the sum for I first or j first. So for example, this one, I'm going to do j first. Then the ai is a constant, so can be moved out. And the bj, I only have the bj is changing if it's taking the sum over the j's. But remember that bj is a disjoint union of the entire space X. So if I take the sum of this and this, then I will just get the measure of the intersection of E and AI, right? So this will just become the sum of AI, j from 1 to q, mu of E, AI, bj. But as I said, this one is just the mu of E, AI, right? Okay, and similarly, this one is just going to be the sum. I'm going to take the I first, then the j. We'll have the bj. The sum I is from 1 to p, mu of a e ai bj. Now the j is fixed, the I is changing, so that's why this whole thing here is the measure of E and bj, because AI will is a disjoint union, forms a disjoint union of the entire space. Okay, And now you can see the first term is nothing but just the integral of f over e. And the second term is just integral of g over e. Okay, and that finishes the proof. Okay, so now we can convince ourselves that the integral defined here is still linear. Right? Now we look at the other properties. But suppose we have a sequence of sets, a sequence of measurable sets. It's non-decreasing or increasing. So usually when we say increasing means non-decreasing. If it's strictly increasing, then we specify that by strictly increasing. And consider the E as the union of them or the limit of them. Okay. And if F is a simple non-negative measurable function, then the integral of f over e is also the limit of the integral of f over ek. Okay, and this is kind of very intuitive because if you know that ek's will grow into e, then you take the integral of f on this ek, and eventually take the integral of f on a larger and larger set, then we should expect to get the f over the union of those ek's or the limit of those ek's. Okay, so that's what the theorem says. Okay, the proof is actually very simple. We call that a simple non-negative function can be written as the sum of let's say aix, I is from 1 to p. Then let's say what the limit is. The limit of this integral ek f, this can be written as, keep the limit outside, just the inside the integral is defined to be this ai mu of ek intersection of ek and ai, right? And you know that the limit can pass the summation and the constant. So this is just from 1 to p in the ai, and then the limit of this mu of ek ai. So now only thing changing is inside the limit, only thing changing is a k. So ai is fixed. Okay, and now this can be written as well, remember that the ek's grows into e, right? So it's increasing. This will be an increasing set as k gets larger and larger. So we know that for this case, the limit can be exchanged with the measure, right? Because of continuity of the measures, and you're having larger and larger sets, so we don't need to worry about the finiteness of measures. So this is always true, even if you're going to have an infinite measure. Okay, and this, remember that ai is fixed, only the ek is changing, and this is actually the union of ek. Okay, so this is actually just the sum p ai, the measure of the union, because as I said, only this one is changing. So you can treat this as the union of k from 1 to infinity, but this ai doesn't change, so you can move it outside. So you have just the e and the ai. And now you can see this right-hand side is nothing but the integral of f over e. Okay, so that's finishes the proof. Okay, so that's basically what you need to know for the integral of non-negative, simple non-negative functions, and they are very intuitive. And the purpose there is to show the integral of general non-negative functions, which is the thing that we're going to consider now. The integral of general non-negative functions. Okay, so as you recall, we used a sequence for any measurable function. Let's consider non-negative functions for now. Non-negative measurable functions, we can use a sequence of simple functions to approximate it, right? Approximate it from below. So we can get a sequence of non-decreasing non-negative simple functions, and they converge to the non-negative function f. Okay, and for each of these simple functions, we can compute the integral as we just showed. And then we want to show that the limit of those integrals will converge to the integral of f. And that is actually how we define this, the integral of f for general function f. Okay, so suppose f is a non-negative measurable function. Then the integral of f on E is defined by the following supremum. So it's the integral of E, integral of f over E is defined to be the supremum of the integral of h, okay, where h is simple non-negative, like what we considered in the previous subsection, and hx is below this f for any x. Okay, so intuitively what this means is, suppose we have a function, say this part is e, and then we have this function defined over e, and then let me draw it more, it has a larger variation. So over this function, over this array e, so we can define simple functions like this. Okay, so these are simple functions. This is a h function, and we can easily get the integral of this h because it's piecewise constant. And then for all such functions simple functions that are below f, we can take their integrals and we see what's the supremum of those integrals, the value of those integrals. That supremum of those values is defined to be the integral of f. Okay, and you can see that's very intuitive because these areas is not, sorry, this area is not as large, but we have the freedom to, or we have the liberty to choose even better approximation of f using a more refined simple function. Okay, and then the integral of that function could get closer to the integral of f. Okay, so intuitively that's the idea. Okay, next we show a few properties of the integrals. Suppose we have two functions f and g. They are both non-negative, general non-negative measurable functions. And f is less than or equal to g everywhere. then the integral of f is always less than or equal to the integral of g. Okay, and this can be easily shown because if we have, for any simple non-negative function h that is smaller than or equal to f, it is also smaller than or equal to g. So if you take the supremum of the integral of h, it should be less than or equal to it should be equal to the integral of f, but it will be less than or equal to the integral of g, because if the supremum for g is taken over even larger set of simple functions, right? So that's why this is true. And in this case, if g is integrable, that means if this is finite, then apparently the f is also integrable, because this is also finite. And also if f is bounded by some constant m, so you don't need to take the absolute value because it's always negative that we're considering here. And the set E has a bounded measure, then this f will be integrable. But because in this case, we can just consider g to be the constant function m over the set E, then the measure or the integral of this function on the right is just the m times the measure of E, and that is a finite number, and that implies that f is integrable. Okay, so that's for the item 1. It's very easy to show. The second one says that if we have a subset A of E, and A is measurable, then the integral of f over A is just the integral of f times the characteristic function of A over E. And that is obvious as well, because if we have h that is less than or equal to f, then apparently the h times Ca, which is also a simple non-negative function, that is less than or equal to f times Ca. Okay, and so for any h satisfying this, it also satisfying this. So we can easily take the supremum over the h. It will be the same as taking the supremum of h here, and they will give us the same result. Okay, so these first two are really trivial to show. I'm going to just show the last one. So what it says is if f is general non-negative measurable function, and the integral of f is 0, then f has to be 0 almost everywhere. Okay, and that is not surprising because if, let's say that if it's not 0 almost everywhere, it takes the positive value over a set with positive measure, then we will get something bigger than 0. The integral must be bigger than 0, right? But to formally show this, let me show this by using considering the following set. Okay, so this set is given by the ek. Define my ek to be the set of points where f is bigger than 1 over k. Okay, this is considered the points in E where the f is bigger than or equal to 1 over k. Then, as you can see, then this ek is increasing in k, right? Because when k gets smaller and smaller, this set is getting larger and larger, right? So this increases. And also, we can see that when we take the integral of f over ek, that should be less than or equal to the integral of f over E, because ek is a subset of E, and f is non-negative, right? So this must be true. And on the other side, over the set ek, f is bigger than or equal to 1 over k. So that's why this is bigger than or equal to the integral of 1 over k over the ek, and this is just 1 over k times the measure of ek. Okay, so if the function has a integral equal to 0 as we given in the condition, then this means that the mu of ek must be 0. Okay, so this means that mu of ek must be equal to 0. While it is 0 for every if z is equal to 0 for every k, then what we have is you take the set of points where fx is greater than 0. What we will need to show is that this set should have a measure 0, right? If this has a measure 0, that means it is 0. The function f is 0 almost everywhere. So let's look at this set. This set is nothing but the union of the EKs, right? Because the EK is defined to be this kind of thing. Okay, so the measure. So since this is true, we know the measure of this set. So I can just simply write this as that, as we usually do. And this should be the measure of the union of the EKs, and it should be less than or equal to k from 1 to infinity of mu of EK. Actually, it's just a limit, so I don't even need to take the sum. I can just take the limit of this. Just take the limit here. Okay, but it doesn't matter because each EK has a measure 0, so eventually you'll get just get measure 0. And this implies that the measure this is already implies that the function f is equal to 0 almost everywhere, right? Because the measure of the set where it is positive is 0. Okay, and finally, this lecture we're going to give the last theorem, which is also a simple result. So suppose my function f is integrable. Then f must be finite almost everywhere on E. Okay, so the proof, so the function is integrable means that the integral is finite, right? And this implies the function must be finite almost everywhere. And this is also intuitive. If it's not finite almost everywhere, that means there exists a set with positive measure and the function is infinite over that set. And that will make the integral equal to infinity. Okay? So that's the idea of the proof. So let's say here we define the set of points where f is bigger than or equal to k. So as you can see, the EK is decreasing, right? And the intersection of the EK will be the set where function f is infinite. Okay? Define, say, A to be set f where it is positive infinity, and this should be the intersection of those EKs, and also the limit of those EKs. Okay? And now, again, taking the same trick as before, when we consider the integral of f over the EK, it should be less than or equal to the integral of f over the E, because the EK is a subset of E. And on one side, I know this function is integrable, so this should be a finite value here. But on the left-hand side, this is over the set EK, the function f is bigger than or equal to k. So that means this is bigger than or equal to the integral of k over the EK, and this is just k times the measure of EK. Okay, so this implies that the mu of EK is less than, I call this constant big C. Okay, and this will be less than or equal to big C over k. Okay. And on the other hand, I know that the measure of A is just the limit of the measure of EKs. And as we showed here, this is less than or equal to the limit of C over K. and apparently this is equal to 0. So that's why the measure of A is just 0. And the measure of A is where it's a measure of the set where the function is infinite. So that's why we show that the function f must be finite almost everywhere.